Flexible pipeline risk assessment, evaluating safety and integrity of pipeline systems. Purpose and scope of flexible pipeline risk assessment, API RP17B and its role in risk management. Flexible pipeline risk assessment is a structured process aimed at identifying, evaluating, and mitigating hazards associated with flexible pipe systems throughout their life cycle. Unlike rigid pipelines, flexible pipes consist of multiple layers of polymers and metallic armors, making their failure mechanisms complex and often hidden. The scope of this assessment includes design, manufacturing, transportation, installation, operation, and decommissioning phases. Each phase introduces unique risks such as material incompatibility, fatigue, corrosion, and operational overload. The purpose is to ensure safety, environmental protection, and operational reliability by applying risk-based engineering principles aligned with API RP17B guidelines. This involves integrating hazard identification, hazard, consequence analysis, and preventive measures into decision-making processes. By focusing on life cycle risks, engineers can anticipate degradation mechanisms, validate design assumptions, and implement monitoring strategies that reduce uncertainty. Ultimately, the goal is to achieve a LARP, as low as reasonably practicable, risk levels while maintaining compliance with industry standards and regulatory requirements. API RP17B serves as a cornerstone for flexible pipe risk management by providing best practice guidelines for design, analysis, manufacturing, testing, installation, and integrity monitoring. It complements API specifications 17J and 17K, which define minimum technical requirements for unbonded and bonded flexible pipes respectively. The recommended practice emphasizes a holistic approach, integrating risk considerations from concept selection through operational life. It addresses critical aspects such as material qualification, prototype testing, and fatigue analysis, ensuring that design assumptions are validated under realistic conditions. API RP17B also outlines methodologies for assessing failure modes, including collapse, burst, fatigue, and corrosion, and prescribes monitoring techniques to detect early signs of degradation. By embedding these principles into project workflows, engineers can systematically reduce uncertainties and enhance safety margins. The document encourages collaboration between purchasers and manufacturers to define system-specific parameters, ensuring that risk controls are tailored to operational environments and functional requirements. Risk-based engineering philosophy, lifecycle risk perspective. Risk-based engineering for flexible pipelines involves a systematic approach. The process begins with defining functional requirements and environmental conditions, followed by assessing potential failure modes such as fatigue, corrosion, and polymer degradation. Quantitative and qualitative methods are used to rank risks based on severity and probability, enabling prioritization of mitigation measures. Engineering controls include design safety factors, redundancy, and material selection, while operational safeguards encompass monitoring systems and maintenance strategies. By integrating risk assessment into every stage of the lifecycle, from concept to decommissioning, organizations can optimize resource allocation, enhance reliability, and comply with regulatory standards. This approach not only improves safety but also supports cost-effective decision-making by focusing efforts on high-risk areas. Flexible pipeline risk is inherently lifecycle-driven, with vulnerabilities emerging at different stages. During design, risks stem from incorrect material selection, inadequate fatigue life predictions, and insufficient safety margins. Manufacturing introduces hazards such as layer misalignment, armor wire defects, and end-fitting sealing failures, which can become latent defects. Transportation and handling pose risks of overbending, crushing, and sheath damage, while installation challenges include exceeding minimum bend radius, MBR, dynamic loads, and soil interaction uncertainties. Operational risks involve pressure-temperature cycling, slug flow, and external interference, all of which accelerate degradation mechanisms like corrosion and creep. Aging further compounds these risks through polymer embrittlement and armor fatigue. Recognizing these life cycle phases allows engineers to implement targeted controls, such as prototype testing, real-time installation monitoring, and integrity management programs. By adopting a life cycle perspective, organizations can anticipate failure precursors, schedule preventive interventions, and maintain fitness for service throughout the pipeline's operational life. Hazard identification and risk sources, design and material selection risks, installation and operational risks. Design and material selection are critical determinants of flexible pipe integrity. Risks arise when materials are incompatible with transported fluids, leading to chemical degradation or blistering. Incorrect predictions of fatigue life under dynamic loading can result in premature armor wire failure. Inadequate safety margins for pressure and temperature extremes may cause collapse or burst events. Polymer layers must resist creep and maintain sealing capacity over time, while metallic components require corrosion resistance in sour service environments. Failure to account for these factors during design can propagate systemic vulnerabilities that are difficult to rectify later. Mitigation strategies include rigorous material qualification, validated design models, and adherence to API RP17B criteria for strain, stress, and collapse resistance. Collaborative reviews between manufacturers and purchasers ensure that functional requirements align with environmental conditions, reducing the likelihood of design-induced failures. Installation and operational phases introduce dynamic and environmental loads that challenge flexible pipe integrity. During installation, exceeding the minimum bend radius, MBR, or applying excessive tension can cause structural damage such as ovalization or armor disorganization. Real-time monitoring and pre-lay analysis are essential to prevent these failures. Operational risks include pressure-temperature cycling, slug flow, and vessel motions, which induce fatigue and increase curvature at critical points like sag bends and hang-offs. External interference from fishing gear or dropped objects adds further complexity. Environmental factors such as seabed instability and marine growth can alter load distributions, while chemical exposure accelerates polymer aging and corrosion of metallic layers. Mitigation requires robust installation procedures, validated dynamic analyses, and continuous monitoring of annulus pressure, temperature, and structural response. By addressing these risks proactively, operators can maintain compliance with design criteria and extend service life. Primary failure modes in flexible pipes, consequence categories, and risk implications. Flexible pipes exhibit distinct failure modes depending on whether they are unbonded or bonded constructions. Unbonded pipes commonly fail through carcass collapse, armor wire fatigue, and sheath breaches, often triggered by cyclic loading or corrosion. Bonded pipes, on the other hand, are susceptible to liner blistering, reinforcement rupture, and delamination due to gas permeation and thermal cycling. These failures compromise structural integrity and fluid containment, posing significant safety and environmental hazards. Early warning signs include abnormal gas venting, pressure fluctuations, and localized temperature anomalies. Understanding these mechanisms enables engineers to design targeted inspection and monitoring programs. Consequences range from minor leaks to catastrophic ruptures, with potential impacts on personnel safety, environmental compliance, and production continuity. Risk assessments must therefore incorporate both probability and consequence dimensions to prioritize mitigation efforts effectively. Consequences of flexible pipe failure extend beyond immediate technical issues, encompassing safety, environmental, and economic dimensions. A rupture or leak can lead to hydrocarbon release, posing fire and explosion hazards to personnel and facilities. Environmental impacts include marine pollution and regulatory non-compliance, which can result in legal liabilities and reputational damage. Production losses from unplanned shutdowns affect project economics and contractual obligations. These implications underscore the importance of robust risk evaluation frameworks that integrate consequence severity with likelihood estimates. By applying structured matrices and scenario analyses, engineers can identify high-risk areas and allocate resources to preventive measures such as enhanced monitoring, redundancy, and emergency response planning. Ultimately, Consequence assessment drives decision-making on design margins, inspection intervals, and contingency strategies. Risk evaluation logic and acceptance criteria, mitigation measures across lifecycle. Risk evaluation for flexible pipelines employs a combination of qualitative and quantitative methods to rank hazards based on likelihood and consequence. Acceptance criteria are typically defined using ALARP principles, ensuring that residual risks are reduced to levels that are as low as reasonably practicable. Uncertainty in degradation rates and inspection coverage must be factored into assessments, often through conservative assumptions and sensitivity analyses. Tools such as risk matrices, fault trees, and probabilistic models support decision-making by highlighting critical failure scenarios. These evaluations inform design choices, operational limits, and maintenance strategies, enabling a proactive approach to risk control. By establishing clear thresholds for acceptable risk, organizations can prioritize interventions and justify resource allocation in alignment with safety and reliability objectives. Mitigation strategies for flexible pipeline risk span design, installation, and operational phases. Design controls include applying safety factors, selecting corrosion-resistant materials, and validating configurations through prototype testing. Installation safeguards involve pre-lay analyses, real-time monitoring, and adherence to minimum bend radius criteria to prevent structural damage. Operational risk reduction relies on integrity management programs incorporating annulus pressure monitoring, temperature trending, and periodic ROV inspections. Advanced techniques such as fatigue hotspot analysis and polymer aging models enhance predictive capabilities. Emergency preparedness, including contingency plans for leak response, further reduces residual risk. By integrating these measures into a comprehensive risk management framework, operators can maintain fitness for service and extend asset life while ensuring compliance with API RP17B and related standards. Inspection challenges and monitoring techniques, residual risk and fitness for service decisions. Inspection of flexible pipes is inherently challenging due to limited direct access and complex internal structures. Traditional non-destructive examination methods are often impractical, necessitating reliance on indirect indicators such as annulus pressure trends, temperature profiles, and gas venting anomalies. Monitoring systems integrated into end fittings provide real-time data on internal conditions, enabling early detection of abnormal behaviors. ROV surveys complement these techniques by assessing external sheath integrity and ancillary components. Advanced diagnostic tools, including dielectric sensing and acoustic monitoring, are emerging to enhance detection capabilities. Despite these innovations, uncertainty remains, requiring conservative interpretation of data and robust contingency planning. Effective integrity management combines continuous monitoring with risk-based inspection intervals, ensuring timely interventions and sustained fitness for service. Fitness for service, FFS, assessments determine whether a flexible pipe can continue operating safely under existing conditions. These evaluations consider residual risks after implementing design and operational controls, factoring in degradation trends, inspection findings, and uncertainty margins. Analytical models estimate remaining life based on fatigue cycles, corrosion rates, and polymer aging, while empirical data from monitoring systems validate these predictions. When risks exceed acceptable thresholds, options include increased monitoring, load reduction, or planned replacement. Decision-making must balance safety, environmental compliance, and economic considerations, often requiring multidisciplinary input. By adopting a structured FFS approach, operators can optimize asset utilization while maintaining integrity and regulatory adherence. Summary of best practices. Flexible pipeline risk management is a continuous process that spans the entire lifecycle of the asset. Key best practices include early integration of risk assessment into design, rigorous material qualification, and validation through prototype testing. Installation must adhere to strict controls on bending and tension, supported by real-time monitoring. Operational integrity relies on comprehensive monitoring systems and risk-based inspection strategies, given the limited feasibility of direct examination. Understanding failure modes and their precursors enables proactive interventions, reducing the likelihood of catastrophic events. Collaboration among stakeholders, designers, manufacturers, operators, and regulators, is essential to align technical requirements with safety objectives. By following API RP 17b guidelines and adopting a risk-based philosophy, organizations can achieve alarp risk levels, safeguard personnel and the environment, and ensure reliable production.